Okay, hope you enjoyed your lunch. If you still have food in front of you, feel free to continue eating. I'm sure there's more out there, so if you're still hungry, feel free to pop out there and get some more to eat. I think I also saw some cookies or brownies or something out there, so help yourself. We're getting ready to kick off the main body of the workshop now after a great morning focused on the core flight software framework. I'll give you some logistical information in a few minutes. Some of you heard that already this morning, but I'd like to introduce Dr. Jim Birch. He's Vice President of our Space Science and Engineering Division here at the Institute. He's been the principal investigator on a number of missions and instruments, and a couple of note is NASA's first MIDEX mission, which was IMAGE, the imager for Magneto's pause to Aurora global exploration, and also the current mission, MMS, the magnetospheric multi-scale mission, which is currently in operations. Dr. Birch was recently inducted into our local Aerospace Hall of Fame and has received a number of other recognitions throughout his career. So anyway, help me welcome Dr. Birch.
Okay, thank you, Ronnie. Welcome to SWRI and welcome to San Antonio. It's my hometown. Weather's typically good. Hope you'll go downtown to the Riverwalk at least once. It's all lit up for the holidays. A lot of activity going on down there. And so we have our division here, Space Science and Engineering, which started in 1977 with one person, me. Now we've got 374 people, and we have three directorates: Space Science, Space Systems, and Planetary Science, which is in Boulder, Colorado, although we have an equally significant planetary science group within our space science here also. So we see ourselves as Center of Excellence for Space Power Systems and Avionics for NASA and aerospace industries, for space instrumentation for NASA and ESA, and for complete space science missions for NASA. So we have several operating missions I can just mention. New Horizons, most people know about. It flew by Pluto 2015, 4th of July. Now it's going to continue out. It has continued out to a Kuiper Belt object, MU-69, now called Ultima Thule. It will fly by there on January 1st, 2019. Left is Pluto. On the right is what we think Ultima Thule would look like. It's much smaller. It's some kind of a binary, and we've determined that by doing a ground-based campaign of stellar occultations. And so all excited about taking a close-up look at the first Kuiper Belt object, and we'll all be camping out at APL for that as a mission operations center. As Juno's been operating for several years now, I mentioned New Horizons, Alan Stern, and our group in Boulder is PI of that mission. For Juno, the first polar orbiter of Jupiter, Scott Bolton of our group here in San Antonio is PI of this mission. This is the second New Frontiers missions. New Horizon was the first one. Juno can look at the interior of Jupiter using magnetometry, microwave radiometry, and gravity measurements. The search is to try to see if there's a solid core, a molten core, or only a gaseous core, and to learn what the thermal distribution of the interior of Jupiter is. And they've gotten a lot of results and being published on a continuous basis. Now this is the microwave radiometer measurements of the Great Red Spot, which is still a mystery at Jupiter. We're able to look deep down into the red spot and see thermal distributions, as you can see in the upper left. Also, being in a polar orbit, Juno can get the first close-up views of the aurora at Jupiter. And this is some of the images from the ultraviolet imager. And so we're finding out the aurora on Jupiter looks similar to that on the Earth, but caused by different processes, much more energetic particles. Now there's a Cygnus, which we implemented completely in project management, spacecraft builder, instrument builder, mission operations, and everything, but we're not the principal investigator. This is for our University of Michigan principal investigator, Chris Rupp. It's been flying now for a couple of years, 8 spacecraft and constellation. Earth orbit, the idea is to look at the intensification of hurricanes. And the story was, we know where hurricanes are going. We don't know if they're getting stronger or weaker because you have to fly right through the middle to know that. You can only do it a few times. So this uses Doppler-shifted GPS signals to measure wave heights. The data look something like the picture in the lower right. And there's a direct correlation between wave height and wind speed. The advantage of this is that it's not blinded by rainfall. In previous techniques were blinded by rainfall. But there's a lot of modeling that has to be done to extract the wave or the wind speeds from these images, which is a slower process, and hopefully it'll be optimized. One of the other side benefits of Cygnus is it's measuring surface water globally between the inclinations of plus or minus 35 degrees. So a polar orbiter mission like this could get global surface water, which would be a very valuable measurement to have. MMS, I know more about, magnetospheric multiscale, since I'm the principal investigator of it. The single objective was to understand magnetic reconnection, which is the process that causes solar flares, causes magnetic storms at the Earth, and indirectly causes the aurora. And we knew going in that we needed to make measurements of particles 100 times faster than had ever been done before, which involved a completely new technique. And so now we've done that. Been in orbit a little over 3 years now. These are the 4 spacecraft. I filled up the Atlas V, didn't have to worry about any secondaries hanging on, which is good. So this is from the science paper, these little circles there, all sky views of electrons. The energy is higher at the outer edge and lower at the middle. And this is the entire 2 slices of the all sky view. And in the middle is a diagram of reconnection, of magnetic reconnection, where on the left, magnetic field lines of the Earth, and on the right, magnetic field lines of the Sun. And where they come together, you get this X point that we've known about. We've, from theory and from other spacecraft, who've gone close enough by to know that this exists, but never been able to probe it in detail. And we've done that. We know exactly what causes the electric fields that cause reconnection to happen now, and we've launched in March 2015. We're getting close to 500 papers published now. So if you're really into magnetic reconnection, there's more than you can read, but a lot of it's pretty heavy going. But here's a movie. But this shows the 4 spacecraft. And on the right of each plot, you can see them flickering around. These are the all-sky images of the electrons. And in the boxes on the left, the line plots, those are things like electric fields, magnetic fields, particle temperatures, and dissipation rates, and all of the things we need to look for to find a reconnection. And so the point of MMS is the previous fastest measurement of this was cluster, which had 1 data point for this 2.5 seconds right here, whereas MMS gets 100 data points for this 2.5 seconds, which is why we could make this movie. So that's what we had to do, and took a lot of flight software. Just go back to that. We had an S-band downlink, so we can only bring down 5% of the data that we're taking. So we have an onboard system with flight software that looks at this data at its fastest rate that is being acquired, and chooses the 5% periods that we can send down to the Earth and analyze. And we have that backed up by people on the ground called scientists in the loop that look at 4-second data, like the average rate of the previous record. So 1 data point per frame like this. Turns out, though, that the onboard system wasn't perfect. We need this scientist in the loop. And so now, after a few years, we're using some machine learning techniques. We're optimizing the onboard software further. And I really think that before too much longer, we won't need the backup on the ground, because the onboard system has the advantage of looking at data at the burst rate, where the people on the ground can only look at summary data. So we've set a lot of records with MMS, a record use of GPS. We're at 12 RE, where the GPS are at 4 RE. It wasn't designed for doing what we're doing. The closest separation between spacecraft constellations is 7 kilometers, a lot of other things. Now, we're under development of several missions. One is Lucy, and this is one of the two of the latest Discovery class missions. The other one being Psyche, and this would be the first one launched in 2021. Flying by the Trojan asteroids. These are asteroids trapped in the L4 and L5 points of the Jupiter. So they orbit around the sun with Jupiter. They were put there when the solar system was formed. They've never gone closer to the sun than Jupiter, so they've never been processed, for example, like a comet has. So this is pristine material. These two of them, two populations. It turns out if we launch at this schedule, the principal investigator of this mission is also from our group. He's in Boulder, Hal Levison, and he came out with a very ingenious way of using trajectories to be able to visit both populations. So this is now in Phase C, in building hardware. The other one we're working on flight hardware is Europa Clipper. There are 9 instruments on, and we have 2 of them here in our group here in San Antonio, the ultraviolet spectrometer and mass specs, the highest resolution mass spectrometer ever flown in space with M over delta M greater than 1500. So we can see a lot of isotopes that weren't able to be seen before. We'll be able to look at the what's in these plumes. Now the plumes at Europa were discovered by 2 scientists here at SWRI, one of which is still here, Kurt Rutherford, using Hubble telescope. And of course they saw these, and then this is one of the reasons why there's an ultraviolet instrument on Europa Clipper now, because they were seen in the ultraviolet on Hubble. Of course, to be convincing, you had to do it again. That's the way science works. Well, they tried it took a couple of years to see it again, but they did see it again. So we're sure these plumes are there, and looking forward to seeing them close up. ESA has a lot of space science missions, and we've been on Rosetta with 2 of the 3 U.S. instruments. That's no longer operating because it landed on the comet, but there's 3 active ones. There's the JUICE mission, Jupiter mission that's mainly looking at Ganymede, which has SWRI ultraviolet spectrometer. There's Solar Orbiter that has SWRI mass spectrometer and a UV imager. And then Bepi-Colombo, which is just recently launched, Mercury Orbiter that has a neutral mass spectrometer from our group here on board. Now, there's some missions in design. I won't mention all of them, but one that's I think pretty interesting is Punch. It's one of the 5 Phase A design studies for the next SMEX. And so that's already been completed, and the selection will be in the spring. The idea here is on the right is the sun, so the coronal mass ejection is coming off. We've seen plenty of those. On the left, the very left edge, is the Earth, where we have magnetic storms. And, of course, this material that goes from the sun to the Earth is completely invisible now. Our PI of this mission, Craig DeForest, in our Boulder group, was able to take stereo data and process it in a lot of very intricate ways, and for one event to make this movie. And so he proved that you can track this material from the sun to the Earth using Thomson scattering of visible sunlight off of electrons. And the movie quit running, but you saw it. And so once this flies here, there are 4 spacecraft, which are the Cygnus spacecraft. 3 of them have the instrument that measures the Thomson scattering of light off of electrons, and the odd one there, the one second from the left, has a NRL coronagraph on it so that you can see the CMEs. And so this mission will be able to look 24/7 at material that is coming from the sun to the Earth, and pretty much revolutionize science of forecasting space weather. So in future, we're always putting in proposals. We have a multi-spacecraft auroral physics mission that I'm putting in. We have a scientist here that's developed a way of imaging oxygen ions escaping from the atmosphere. Never been done before, and that's just been submitted. We've submitted a Pathfinder for MagCon, which is a mission that's been around for a long time, hasn't been implemented yet, and we're working on several Discovery mission proposals. Now, on the non-NASA side, a spacecraft constellation is a big thing now, and it involves a lot of flight software. This is either for commercial data or defense data, And you probably know that some of these constellations have cyber connections, either both between and among the spacecraft, but also to the cloud, and using also artificial intelligence. And so we're working on that because we have the experience with constellation, we have the experience with avionic systems, and the other another division here called Division 10 is our our flight software group for the most part, and they're going to collaborate with us on this. So that's my 15-minute version of my 2-hour talk, and I can answer any questions you might have. Yes, sir. Well, I had 2 phases. We had a 12 RE and a 25 RE, a dayside mission and a nightside mission. And now we have enough fuel left to maintain the tetrahedrons for 30 more years. And so we're not going to change the orbit. We don't think we really can do things and want to for 30 more years. If we could think of something good to do with that fuel to change the orbit to a better one, we might do it, but we haven't come up with it yet. Cool. Sir.
Hi, I'm Justin McNeil from Aerospace. Just curious, your planetary science directorate in Boulder, how many folk are up there in comparison to here?
Yeah, out of this 374, we actually have 10 in New Hampshire, and we have 90 in Boulder, and the rest are here. So 270 or something here, but yeah, about 100 elsewhere. Boulder is pretty heavy concentration. 90 people, I think 80 or more PhDs in that group. Yeah.
Any other questions for Dr. Birch?
Okay, thank you. Enjoy your meeting.
No, just manual is fine. Where's the clicker?
It's right behind you.
Okay. We had such a large turnout already this morning. Most of you may have heard a lot. It's on timings again, Melissa. Melissa disappeared, so I'll try to control it here. I'll fight the timings here. So most of you already seen a lot of the intro, but I wanted to give you a little bit of logistical information. Most of you are here, so you know how you got here, presumed, but the front gate is over here. You came in this road here. And so as you can see, we have quite a large campus, about 1,200 acres. I think it's larger than that now because we bought some more land, but so quite a large facility. To give you an idea of, you all ate, so you know where to get food, and probably most of you by now have been to the restrooms. They're just right outside this, on the other side of this wall. As I mentioned before, we have some splinter rooms available. If you do need to have a splinter meeting, we have a room just to the left outside these doors. We have another one just outside this door in the back, and then we have another one straight up the elevator, right across from the elevator. If you need to have a splinter meeting or need a quiet place to do something, please check in with one of our admins, and we will. Oh, okay, she's fixing it. And they can point you to an available one or reserve one for you if you need that. Okay, so we have a smoking area right out here outside the building here. And we have the exits, emergency exits out this door, and then down the hall to the left. Out this door, you can go to the right or straight out. In case of an emergency or a fire, we do have next slide. We do have a sort of a mustering point that's basically out behind the building out here in the far end of the parking lot there. Next slide. Okay, great. Again, if you're an international visitor, a non-U.S. person, you should have filled out a foreign visitor form as well as have a foreign visitor badge. If you don't have both of those things done, please check in with our admin assistants out at the registration desk, and they'll get you fixed up. And then also be sure, yeah, we're still on the auto timing. Also be sure you turn in your badges at the end of each day. And then again, just a reminder to our presenters, since we do have foreign visitors in the audience, we want to be sure and make sure your slides don't have any export or ITAR control information. Hopefully you found our wireless network already. It's the SWRI guest. You don't have to authenticate. Of course, we have power on the tables, at least if you're at a table, which most people are. Fortunately, we're able to accommodate the group with most people at a table. Again, most people have cell phones, but if you need access to a phone, check in with our admins. We also have some printers available if you need to print something. If you are a presenter, by the way, please watch the agenda, and when it's getting close for your time, if you'll come up and check in with Melissa, and she'll get you outfitted with a wireless microphone for your presentation. We do have some shuttle transportation available if you're staying at the hotel that offered us a discount for workshop attendees, which was the Courtyard by Marriott. They do have a shuttle service available, departing around 7:15 in the morning from the hotel to bring you here, and then it departs here at 5:30 back to the hotel. I'll give you updated shuttle schedules each day because, for example, tomorrow night we'll have our happy hour at Biggs. We'll also have our dinner on Wednesday night, so I'll give you some updates on that. Or if you have any questions, again, check in with our registration desk, and they can give you that information. There may actually be a printout out there, too. I'm not sure. We also have a couple of Institute-owned shuttles to take you to the happy hour, the dinner, or other places if you need that. If you do need shuttle service, please check in again with the registration desk, and we'll make sure if we can accommodate you. Let's see, I covered that already. Meals, we've already eaten. Hopefully you got enough. If not, head back out there. We've probably got some leftovers or some desserts. And tomorrow we'll also have breakfast and lunch, again, served here each day. Thursday we'll have breakfast but no lunch since we wrap up around lunch. A couple of agenda updates. Tomorrow, our keynote in the morning had to cancel fairly recently. In lieu of that, I have a gentleman here at the Institute that's going to come and present a history of Southwest research. We have actually pretty interesting history of how the Institute was started and some of our involvement in things over the years. I think it'll be very interesting, some old historical footage for you to see, so hopefully you'll enjoy that in lieu of our keynote speaker for tomorrow. Also for tomorrow, there was a presentation by Paulette Atchison at 1:20, I believe, and she had to withdraw just over the weekend, and so the agenda will be adjusted for that. And finally, once again, I want to thank our sponsors. We couldn't put this on without our sponsors. They provide a lot of funding to help pay for a lot of things that, even though we are a fairly low budget and informal workshop, still cost money, so we appreciate our vendors, our sponsors. Please visit their booths out there at the breaks and lunches and other times. We appreciate that very much. And with that, we do have, traditionally, we have some door prizes, so I'm going to give one or two of those away. You do have to be present to win. So I apologize to our remote attendees. We also don't allow our committee members to receive a door prize, so if I accidentally call a committee member, which I'll try not to, but if I happen to draw one, please, we don't want our committee members getting the door prizes. Also, our sponsors are also excluded from the door prizes. I'm sure some of these door prizes are donated by our sponsors. They probably don't want to give the sponsor next door the door prize that they donated. So if I happen to call a sponsor name, if you'd please let me know. So other than that, we'll go ahead and give away a door prize, and then we'll get started with our agenda for the day, for the afternoon. Let's see, I think we're going to have MathWorks come in. There we go, right there. So one of our sponsors, MathWorks, has put together this duffel bag, and I will give you the mic and let you talk about it and then draw.
All right. So in this duffel bag, we have a T-shirt, hat, and several other surprise goodies. Hopefully you'll enjoy them, wear them proudly.
Okay, go get the bucket.
All right, going out to JST, Tam No.
Okay, for our second door prize, we have a Libre computer board.
Chris Landauer.
Chris Landauer? Okay, we'll check, see if he's in the lobby. I'm not sure. I think I saw his name tag still out there. Okay, I think I saw his name tag still saying. Okay, let's draw another one.
Oh, no. Does he go back in? Right down in there. Alan Brown.
All right. Okay, first up is our own Chad Leffler from Southwest Research Institute, going to present on CubeSat versus science instrument complexity. So Chad's on his way up.
Hello, I'm Chad Leffler from Southwest Research Institute. My previous two projects have been science instruments, and now, if I can get this thing to work here. Now I've been put onto a CubeSat, and so I'm going to compare whether or not there's really all that much difference between a low-budget CubeSat versus a complex science instrument. So my previous two were Stellar Orbiter HIS and Juno Jade. Now I'm on CUSP, and CUSP is also similar to Cygnus, so I've included it here too. In terms of the actual processor boards that the software has been running on, they're similar enough here. 3 of these are 4 megabytes of SRAM. One of them had 16. MRAM has been half a megabyte to 2 megabytes. The processors have been anywhere from 24, 25, 50 megahertz. Similar enough range on here. The CubeSat and SmallSat, Cygnus and CUSP, both have 4 gigabytes of flash each as well from their mass memory storage of their telemetry to downlink. For operations of a science instrument, it's receiving commands and sending telemetry. It's going to perform fault management and detection, collect and process science data, including use of high voltage for its sweeping and scanning. The operations planning has to handle reacting to certain operations like thruster firings and orbit change maneuvers, but not how to accomplish them. The operations planning has to focus on the data production that the instrument produces going to the mass memory, but not on the actual storage and downlink to ground. And instruments don't always have heater control. That's usually done by the spacecraft, at least on the ones I've been on. For the CubeSats and SmallSats, they control the radio for the uplink and the downlink, which the instruments just take for granted. They also process commands and telemetry, perform fault management and detection. The CubeSat SmallSat is in charge of the thruster firings and orbit change maneuvers, and they've got the ADCS components, attitude determination control system, for pointing and stability. They maintain the heater control of the payload, the instruments, the rest of the spacecraft. They maintain the power levels and battery charging, and they store all the data in their mass memory, handling the partition and the downlink. From the software perspective of this, though, while it seems to be a little more complex, at least as far as the software I have on the CubeSat, it's partitioned out such that the individual components, such as the ADCS, the power system, and the radio have their own internal software as well. So I don't have to know, for example, on the downlink, what the carrier waves are, what the modulation and encoding are. I write a CCSDS packet to the radio, and then it handles that in its own software to send out. And as far as the ADCS, I tell it, okay, go sun point, go earth point, detumble, desaturate, then its own internal software does that as well. So I still don't have to worry about those deep internal complexities with the CubeSat software. For the fault management for really CubeSats or instruments, they isolate faults to the lowest possible level. For the science instrument, if the fault is contained within a single sensor and there are multiple sensors on that instrument, then it can safe that particular affected sensor but leave the others in their science mode to preserve some science data. For an off-nominal situation that's not critically dangerous, where there is some isolation, but it's not going to do any damage, then there's a safe mode. It'll turn down all the high voltage, stop science data collection, and turn off the individual sensors such that only main electronics are running at that point. For something that's critical or dangerous, then the instrument, usually unable to turn off its own power, will send a request to the spacecraft asking to be powered off. For the CubeSats and small sats, they are fail operational as opposed to fail safe. So for most components, except for the payload, the components are critical and they must remain operational, even if only in a minimal capacity. The radio, the power system, and the ADCS all need to be as operational as they can be. Faults usually result in the payload instruments being turned off as they are not critical for the mission to save itself. And safe mode usually means sun pointing as opposed to earth pointing. For testing and integration for these science instruments, we usually test with the single spacecraft interface simulator or emulator, and we have minimal external interfaces to the spacecraft or component between instrument and spacecraft. For Juno Jade, for example, I had 2 serial interfaces to the spacecraft. For HIS, I had a spacewire interface to the spacecraft and an internal optical link interface. We can have multiple internal interfaces, some with different protocols. And the sensors and detectors, which are part of the instrument, go through science calibration and beam testing. For the CubeSats and small sats, we have more interfaces, and we have more components to test with. So we've got multiple instrument interface simulators or emulators, and we've got multiple spacecraft components to test with. Each of these interfaces may have different software or hardware protocols. So for example, on CUSP, I have a SPI interface to my radio. I have I2C interfaces to one instrument, the power system, and a real-time clock. Then I have serial interfaces off to the ADCS system, the GSE interface, and one of the other instruments. So that adds to the integration and testing time as well as the complexity of from that perspective. As far as the stakes of destruction, for the science instrument, it can override its non-volatile memory with junk data and have no software to run. It can improperly use high voltage and cause loss of science capability in the sensors and detectors. There could always be a low voltage short circuit in the main electronics or a component that does not have switchable power. Or it can mass produce too much data and fill up the spacecraft mass memory and not allow any of the other instruments to send any data. But even with all of that, a properly isolated science instrument is only going to end in its own destruction, not the destruction of the payload or the spacecraft. Usually the instrument has power being drawn from a switched source on the spacecraft, and there's monitoring of its power draw. So if there's a problem with the instrument, it can be powered off without the rest of the payload being powered off. And mass memory is usually partitioned in some manner such that one instrument can't override all the other instruments partitioned. For the CubeSat and SmallSat, software could always fail to deploy solar panel arrays or not charge the batteries. It could fail to detumble and keep spinning away. It could enable maximum power draw and point away from the sun, discharging its batteries and eventually powering itself off. It could fire thrusters for too long or too little and not be in the right orbit or attitude. It, too, like the instrument, could override all of its internal memory and have nothing to boot from, or have a low-voltage short circuit. So most of the faults, at least the major ones inside the CubeSat or SmallSat, are going to end in some loss of the mission of the spacecraft or the payload. So my conclusion here is that the stakes are a lot higher for the CubeSat as far as what can go wrong and what has to be handled from the software perspective and making sure things go as right as possible. And the complexity of the operations, fault management, and testing are higher for the CubeSat. For the software processing needs, they are similar enough such that a common processing board architecture, CPU, memory can be used without it being drastically different. And from the software perspective, a lot of it is still algorithm-based, transforming inputs and moving data around between different buffers. I'm not completely done yet with my CubeSat instrument, so I can't say for final whether software is drastically different or the same, but right now I don't see it as being too drastically different. Are there any questions? What type of radio are you using? The JPL Iris radio.
I guess the question was, what type of radio is the CubeSat using?
And is the JPL Iris radio.
Thanks.
Yes.
Any other questions here? Okay, thanks, Chad.
Okay, next up we have Alan Cudmore of NASA Goddard to give a presentation on high-performance spacecraft computing middleware. Oh, you got one.
Okay, is this on? Can everybody hear me? Is it on?
Should be on. It takes a couple seconds.
Okay. Oops. Yeah, it's falling off. Okay, can everybody hear me? All right, so this is my first non-CFS presentation in a long time. So I'm here to talk about the high-performance spacecraft computing chiplet middleware. Is it not working? Okay. I think I got it.
Okay, yes, that's perfect. Sorry about that.
That's okay. All right, that's much better. Okay, so first of all, as you can see by the agenda, my talk is about the middleware, which is a set of software libraries we're creating for this new high-performance spacecraft computing chiplet. But as you can tell by the agenda, that I have to get through quite a lot just to get the middleware in the right context, because this is a pretty complex device. First of all, what is the HPSC chiplet? So I guess the goal of the chiplet is to dramatically advance the amount of computing power we have for space missions. It'll give us nearly 2 orders of magnitude of improvement above the current state of the art that we have for space processing right now. And it also has a lot of flexibility in terms of power management, fault tolerance, and things like that. And we believe that it can really meet the needs of a lot of different mission use cases. These advances will provide game-changing improvements in the computing performance, efficiency, flexibility, and it will dramatically increase our capabilities for onboard processing. The HPSC chiplet is funded by the Space Technology Mission Directorate, the Science Mission Directorate in the Air Force. And the project is managed by JPL, and the contract is managed by Goddard. And of course, the middleware that I'm going to be talking about is, it's funded by the Air Force Research Lab, and it's a joint project between Goddard and JPL. Okay, so HPSC, I'm having trouble with this thing. HPSC is a contract that was awarded to Boeing, cost plus fixed fee. So under the base contract, they're going to provide prototype radiation-hardened processors, which are referred to as chiplets, in the bare die and packaged parts. They're going to give us a full set of system software, a prototype system software and operating systems to operate on all the processors on the chiplet. They're going to develop the evaluation boards to allow us to test the chiplets and develop software. And they're going to provide emulators as well. There's an FPGA-based emulator, and there's a software-based emulator. There's a bunch of contract options, and the ones they've chosen are the level 3 cache memory. They added a real-time processing subsystem consisting of 2 ARM R52 processors and also a single A53 processor. They added time-triggered Ethernet, SpaceWire, and of course they're packaging it for space applications or qualification. The first chiplets are due in April of 2021. So here's this, believe it or not, is kind of a simplified block diagram of the chiplet. I'm going to go through the major subsystems in the next set of slides here. So starting out here, we have what's called the torch. It's called the Timing, Reset, Configuration, and Health Controller. This is a triple modular redundant ARM Cortex-M4 processor, and it kind of manages the booting of the chiplet and the power management and fault monitoring. So this is sort of our simplest processing device on here, and it's supposed to be the most radiation hardened. And so this will kind of be the watchdog for the whole system. It kind of gets the boot process going. And as you can see, it's pretty complex in terms of booting this. Considering this is just one processor, there's a number of different bootloaders, operating systems, firmware on this thing. Okay, the next major subsystem is called the RTPS, or the Real-Time Processing Subsystem. This consists of a dual lockstep ARM R52 running at 600 megahertz. It has 3 1 megabyte tightly coupled memories for high-speed access. It also has FPU. And it also has this, let me see if I have the laser, a single Cortex A53 64-bit processor with 512K level 2 cache and 32K of instruction and data cache. And of course, it also has FPU. And a key thing about this RTPS is it has its own separate PCI Express and DDR3 and 4 interfaces. So we can kind of isolate the RAM that this subsystem is using compared to the main clusters that we have over here. And so this is where the real-time high-performance flight software, the safety-critical or the mission-critical software will run on the RTPS. So over here we have, this is kind of the main computing horsepower. We have 2 A53 quad-core clusters. So we have a total of 8 ARM A53 processors running at up to 800 megahertz. I think they're still characterizing the radiation and power. Shared 4 megabytes of level 3 cache. Quad shared 2 megabytes of level 2. And of course, 64 kilobytes each of instruction and data cache. And again, FPU. So as you can see, we have a lot of processing power on here. the M4 will mostly run the firmware that's delivered to control the system. But then, flight software or mission has complete control over how to use the RTPS, basically the 3 cores that are available on the RTPS and the 8 cores that are available here on the high performance system. We also have the DDR interfaces. So as I mentioned before, we have the completely isolated DDR interfaces for the RTPS for fault isolation. And then we have another interface over here for the high performance system. And then, of course, we have plenty of non-volatile memory interfaces that aren't shown on this. In terms of high-speed I/O, we have 6 rapid I/O ports, 4 lanes per port. So that's plenty of bandwidth there, 59 gigabytes per second of I/O bandwidth. We have an embedded serial rapid I/O switch with 2 internal endpoints. We have 2 Generation 2 PCI Express ports at 2 lanes per port. Of course, that's 10 gigabits per second per port, so that's 20 gigabits per second of I/O bandwidth. 3 time-triggered Ethernet ports, 2 SpaceWire ports, and of course the general purpose Ethernet port. And we also have a selection of low-speed I/O, including like JTAG, UARTs, I2C, SPI, and general purpose I/O. And in addition, not shown on the chart there, we have EDAC with memory scrubbing. Critical logic is triple mode redundant. It supports the ARM trust zone for the A53 processors. And we have these access isolation regions. So essentially, there are, not shown in the diagram, were the ARM IP for the MMUs that we can use to program to isolate I/O and memory regions. And of course, we have integration with the ARM core site debug and trace system. And so that's kind of a quick overview of the hardware. So now, in order to use this very complex device, the contract includes the delivery of a full suite of prototype system software to take advantage of all these resources. And of course, have you noticed the processors themselves are, they're very popular, the ARM architecture, and there's a lot of open source software available for them. So it's not like a unique, crippled architecture in any way. These are fully compatible with all the open source and commercial operating system offerings out there. So anyway, the chiplet's going to be delivered with the full complement of the prototype system software. It's developed by USC Information Sciences Institute. And they're leveraging a large complement of open source software, including all the libraries, operating systems, compilers, debuggers. They're building their simulator from the open source software. And a lot of the software will run unmodified on these processors. The system software consists of board support packages for both Linux on the A53 quad-core clusters, RTEMs on the R52 and the M4, a complete set of development tools, including an Eclipse-based IDE simulator. They have a QEMU-based simulator. A set of APIs for configuring the chiplet, so they'll have software running on the M4, and we'll be able to make calls to that to do things like power management, fault management, things like that. Excuse me. And of course, that'll be done through the Mailbox API. And they're offering software-based fault tolerance libraries. There's a number of open source libraries available for Linux so you can do software-based fault tolerance. And they're planning on trying to leverage as many of those libraries as they can, like for checkpoint and rollback in Linux. And they're also planning on even implementing the KVM hypervisor software for the A53s. And then, of course, the chiplet emulators. And so they just want to provide like a full reference system that a mission can either use or use as a reference system for porting additional software. This is kind of just a picture of the system software architecture. So we have the hardware on the bottom here, and then showing on the A53 8 cores over here, the two 4-core clusters. We have a full 64-bit Linux running. They're using Yocto Linux, which is one of the embedded Linux distributions. And they also plan on delivering the KVM hypervisor. And then on the microcontroller side, the Torch M4, which is the system controller, they're using RTEMS on that. And then the R52 is also going to have RTEMS. The real-time processing subsystem, the RTPS, it also has this extra A53 that was kind of added to the contract, but the system software did not include an operating system for that. So that's one of the things that Goddard and JPL are considering is obtaining the additional funds for porting an operating system to the single A53. And then, of course, on top of the operating systems, they're going to provide their fault detection and power management and configuration management APIs. So let's see, I probably mentioned a lot of this, that they're just using the Torch Cortex M4 is going to have RTEMS, and it's going to have support for the serial rapid I/O, all the low-speed I/O, of course, the configuration registers, and it'll have windowed access into all the memories. And the RTPS, the real-time processing subsystem, the R52 will also execute RTEMS, and it'll have support for most of the high-speed devices, and also windowed access into the high-performance processing subsystem DDR and NVRAM. So there's a lot of features built in here to try to manage the fault tolerance and the reliability of the system. And then, of course, the high-performance processing subsystem, the A53 clusters, they're going to run Yocto Linux out of the box. And there's going to be built-in support for all of the high-speed I/O devices that we have. And I think this goes without saying that, there's tons of software available for running on top of Linux. Just a simple example of how fault tolerance could work in this system. So given that we have completely isolated RAM from the high-performance subsystem and the real-time processing subsystem, like if we were just running Linux on here and some kind of, non-Class A image processing software or something, some sort of AI algorithm, and we have a fault, it's designed, the chiplet is designed to provide the barrier, the subsystem isolation, so that it doesn't affect the real-time processing subsystem with the real-time mission-critical software for controlling the actual the satellite. Okay, so now we're finally getting to the middleware, which is what I'm working on. So the middleware is funded by the Air Force Research Lab, and they're funding Goddard and JPL. We're developing this as a joint project. And our goal is to provide a layer of software that provides higher level services for flight software applications. So we're getting all these generic operating systems and libraries to control the device and start porting software to. So the middleware team is trying to take this one step further and provide some of the features that we think we'll need for flight software on this device to manage this device. And so we're going to have services that include configuration management, resource allocation, power and performance management, APIs, higher level APIs to manage the fault tolerance. And so we're going to try to make it easier to write flight software for this device by leveraging a lot of these services and hardware resources that are available. And this is kind of extending the layered architecture where we have the system software and then we have our middleware kind of running on top, and then of course the mission flight software. So the middleware is going to provide a few of these key functions: boot and load services, chiplet configuration management, power states, whether or not cores are powered up or down, chiplet resource allocation and management, how all these I/O devices are connected and what cores they're connected to, fault tolerance and redundancy management, and a higher level messaging service. And to do that, we identified 13 middleware services. So we have the deployment and multi-core programming services. So it's essentially, it can be thought of as almost like our OS abstraction layer, or we're providing services to create threads and tasks and spawn processes on certain cores. We're also going to we're going to try to take advantage of like Linux MPI libraries and OpenMP libraries as well for multi-core programming. We have machine information services, which is kind of a suite of API calls to obtain all the device information and status information. Like if you've ever dumped the device tree from a Linux system, you can find out kind of the current state of everything, what type of memory you have attached, what kind of I/O. And so we're going to try to allow both onboard programs and ground systems operators to basically get a dump of the state of the machine in order to see how things are configured, how things are working, things like that. Resource management and arbitration services. We have a number of different I/O devices. Some of them are assigned at boot time. Some of them can be assigned dynamically for this high-speed I/O. And so we're going to try to make a set of APIs to help manage that. We have memory management services because there's like several MMUs on the system, and a lot of different memory resources available on the different buses. And we have to try to manage the memory as well, configuring the MMU so we can allocate it to one processor to keep it away from another processor. We have interrupt services. There's countless interrupt sources on this thing. And then, of course, timing services, too, to synchronize and distribute time. And then, of course, we have messaging services. So not only do we have to provide a software bus-like messaging feature for, say, two different processes or tasks on the same cluster, but we also have to have messages that go between the real-time processing subsystem and the high-performance system. Of course, another very important thing, especially for a device this complex, are debug and trace services. We need to be able to manage the ARM core site interfaces, and we need to try to collect, of course, metrics on what's going on. We have an identified service called the boot and load process and configuration service. And right now, that consists of an initial program loader. You can think of an initial program loader as sort of like in a CFE world, CFS world, the executive services, where it reads a startup table and starts up all the applications. So that's very similar to this. And then we have peripheral I/O services. Let's see what else. And of course, it's probably going to take a long time just to really manage the complexity of a single chiplet, while we're planning on extending this for multi-chiplet management, because using things like serial rapid I/O, you can actually talk between multiple chiplets and network them together using all these high-speed interfaces, time-triggered Ethernet, serial rapid I/O, SpaceWire. There's a lot of potential for high-performance systems that have multiple chiplets, whether it's for redundancy or even more performance. And then, of course, we're going to have some fault and redundancy management services as well for managing the fault detection for both hardware and software faults, and some of the recovery services to manage that. So that in a nutshell is what the middleware services are about. As you can tell, it's a lot of software for a pretty complex device. And here's some of the use cases that were identified for the high-performance spacecraft computing chiplet. There's a use case of a rover that needs a lot of extra performance over what's available in the RAD 750s that are being used today. High rate for science data instruments, the high-speed I/O, very tight control loops, plenty of memory and processing power. And of course, so they're planning on having like vision processing, high-speed motion and motor control, onboard planning, high-performance science instruments and data processing. So there's all kinds of needs for this type of computing power for, another generation of this type of rover. And of course, landers as well, they have real-time compute requirements where they have to have high-rate sensors. Obviously, they have to be very fault-tolerant. And of course, we have other use cases like high-bandwidth instruments where maybe not so real-time and not as mission-critical, but as we know that the imagers and some of the instruments that we're producing now can generate a lot of data. And the ability to process some of this data on board, especially if it's very low or limited bandwidth telemetry, that becomes more important to be able to do more and more processing on board. And of course, we could even imagine using this in a small sat use case where we keep things powered down or, kind of clocked lower and just use the chiplet resources that we need. But we can really host so many of the software subsystems on this chiplet. We can have the isolated GNC and CDH, and then have all kinds of sensor data processing or even autonomy on the cluster. And then, of course, multiple chiplets can be used. This is a scenario of the notional two-fault tolerance system where we have a number of systems tied together with the time-triggered Ethernet, and it can be used for a fully redundant system. This was the example for the human exploration and habitat and gateway style use cases. And of course, it provides us with an order of magnitude higher computing power, and at the same time giving us the data buses that we need to do the fault tolerance. Okay, so they're already kind of planning ahead of what they can add on to this ecosystem of the chiplet. I mean, even though we're years away from getting the chiplet, they're already looking at things like advanced spaceflight memory, increased RTOS support, which includes something like, porting the Green Hills integrity to that single core A53 on the on the real-time processing subsystem, the RTPS. They're talking about, what kind of coprocessors can we have communicate with this, like GPUs. I know the Air Force is interested in, and NASA, in the security features of the chiplet, like, fully supporting trust zone. And then, of course, they're talking about some advanced packaging concepts where you could put multiple chiplets in a package. And of course, NASA would like to develop a single board computer that serves as kind of like a reference board for this type of device. So, so basically the HPSC is driven by the use cases that the future missions could demand. Having all this extra horsepower means we can have much more computational performance on board. Of course, we can take advantage of the energy efficiency and all the fault tolerance features of it. And so the middleware that we're working on, you know, our goal is to try to make this easier to program. You know, we'd like to be able to just easily host our flight software applications, taking advantage of the middleware and the system software that's delivered. Just a little bit about the status. You know, I mentioned that the devices won't be delivered until at least 2021. Currently, the system software team is cranking away at the software releases. They already gave us their system software release 1 and during the May 2018 PDR, and that consisted of the Yocto Linux and a QEMU-based emulator for at least the high-performance computing part of it. And they're actually gearing up for system software release 2, which will add even more to the emulator. I think they're planning on having the first release of the R52 in this next version of the emulator. And they have the 8 cores in the QEMU emulator, so we can actually run and use the 8 cores right now in the system software that they delivered. We're working to try to also come up with our first release of the middleware this month. We're basically just doing our very first subset of our services. And of course, they're mostly just targeting the A53, the high-performance subsystem. And of course, we've planned a series of releases over the next couple of years after that. And so overall, you know, this is, to me, as a, you know, an operating system and technology fan, this is really a fascinating project to me because it's just, you know, you can hardly pack more IP and processors and devices in one chip. And to have this chip with 10 cores running at least multiple 3 or 4 operating systems at once and multiple bootloaders, it's kind of a dream and a nightmare. And so, of course, you know, down here are some acknowledgments, because most of these slides were made by other people, including Jonathan here, who had a lot to do with the initial, the RFP for the contract and everything, and others at both Goddard and JPL and Boeing. So I can't claim to be an expert in the hardware, and I'm learning more about the software, but I'd be happy to answer any questions about it.
I know you said not the hardware, and so maybe you don't know, but do you know off the top of your head what the power requirements are for that puppy?
Yes, there are. I don't know them off the top of my head, but I can find them and let you know. I mean, we do have power numbers for this thing. In fact, I remember 10 watts, Jonathan saying, and not every full bore, of course. Right, and I believe, you know, they're publishing charts that basically are tables that say, you know, when you have these devices powered at this speed, it's taking this many watts. When everything's running at full bore, it's taking this many watts. I think they have like a 1 watt survival use case.
Yeah, but that you wouldn't be using it in the 1 watt survival case. I mean, you're talking about you want all the cores going and all the processing, so that's one that's the more interesting case.
Yeah, I agree, but I think what they're trying to do is characterize it from that 1 watt case all the way up to full bore and provide estimates for us. But we'll try to find out.
Alan, when your architecture figure that was like the second or third slide, it implied that the 2 I/O blocks are accessible to all the cores. Right there.
Right there?
The high speed and the low speed look like they're accessible to all all four processing subsystems.
Mm-hmm.
So does that become a system integration issue to decide who talks to what?
I think it is, yeah. I think you have to have both configuration files at boot time, and then, of course, you know, what things are configurable at runtime that haven't been already allocated at boot time need to be set up by these system software and middleware services. So in other words, you know, phase one is probably setting up your device trees so that you're allocating a certain number of devices to this processor, these devices to this processor. And then, you know, the trick is, I guess, to be able to know when you boot up what devices are allocated to the processor you're running on, and then, you know what configuration can be done with those devices from there.
And so somebody's going to program a system MMU to hide them, or is it just a gentleman's agreement?
I think it's...
Yes. Jonathan nodded yes.
I think we don't know enough yet to... You know, anything this complex, the more I look at it, the more questions I come up with. So it's like, I think what we have to do is make something work on it and learn from what we've done, and then do the next phase, and then we'll say, hey, now we know how to work with it in a basic way. Now we can try to, you know, configure it even more intelligently or whatever. So I think it's going to take a long time to really fully utilize the capability of this thing.
I have a question about survivability or low watt use cases. Is this, because I noticed you had landers listed as use cases. So are you familiar with other studies or architectures that this would be perhaps most comparable to, where you have use case, deep space, low wattage requirements, but the need for high fault tolerance?
Well, yeah, I mean, this is really, you know, this is really of great interest to our partners at JPL on this, and, you know, that's one of their big use cases is the fault-tolerant deep space devices, and, you know, of course, power is always a primary concern for that as well. So I can't claim to know all the potential architectures for it, but I believe that is one of the planned use cases.
I know that we're working with a chip that involves some programmable logic. Is there any kind of plans to integrate that at all within this architecture?
Yeah, I don't think this chip has any programmable logic in terms of FPGA resources, so that seems to be the only thing it doesn't have.
See, another question back here.
Are there any plans to open source any of this middleware software or publish any information on the integration points with it?
As far as the middleware is concerned, that should be a goal, but I don't think there are any plans for it right now. System software is definitely going to be open source. You know, personally, I don't see any reason why the middleware couldn't be open source, but we'll just have to work. We'll just have to discuss that among the team and see if we want to make that one of our goals. But system software is actually going to be open source. You know, Joel over here is involved in creating the RTEMS PSPs for it, and the system software team at ISI is actually doing the development on GitHub, so they're already open source. And I'm not sure if, you know, any type of IP-related things will creep into the system software that will prevent them from publishing every release as open source, but we'll see if it continues. We would certainly like to see the middleware open source at Goddard, just, you know, because it fits in with our philosophy of the CFS.
Okay, we got time for maybe one more, if anybody has one. Back here.
And how about like a roadmap as far as, how much community involvement versus, you guys want to go a certain direction before that happens? What are your thoughts on that?
In terms of the middleware development?
Both.
Of-
Both the middleware and the system stuff.
Okay. Yeah, that's a good question. I mean, right now it's kind of being developed with the input from the working group, which consists of, Goddard. I know JSC has some input, JPL, of course, and the Air Force. So I'm not sure what it would take in terms of opening it up to like a CFS-like development as far as input and community. I mean, I guess maybe, Jonathan, maybe we can try to find out if there's any points where people can provide input to the roadmap, or, we need to find out what's available to both internal and external to NASA.
Yeah, we can. I don't know if this mic's on. Sounds like it. So we're looking into how we can do that. One of the points of this presentation was to get it out in the wider community, to maybe bring some. You can email Alan with different use cases you might have. Because we went through, different NASA centers and the different use cases that NASA and the Air Force can come up with, and sort of plan for those, like power scaling and long cruise phase, and there's fault isolation within the chip. And if you need redundancy, you can have two of them and use Cerio as the cross-channel data link, and all these kinds of things were thought about when we were coming up with the original chip design, or chiplet design. But, we probably didn't cover everything because we have our own focus on our deep space missions. And but in theory, you could use this for a CubeSat as well. I mean, it's a system on a chip with a lot of capability. And if you can deal with the fault aspects, it's supposed to be highly reliable, but, if you only have one, you got one fault containment region, end of mission. So anyway.
Okay, thank you very much.
Okay, thanks.